All right, so this week, both today and Wednesday, we're going to continue talking about sketching algorithms for linear algebra problems like regression, low rank approximation, etc. So last time we talked about, actually, they should have said subspace embeddings, not OSEs, subspace embeddings. So last time we talked about, how do you get a subspace embedding? And there were three ways. One is if you actually have an orthonormal basis of the subspace, let's put those in the as columns of a matrix U. Then U transpose is basically the best subspace embedding you can hope to have. It has D rows, which you can't even get down to D minus one. D is exactly the right, the best you could hope to do, and it has no distortion whatsoever. Just the trouble with that is it's computationally expensive to compute U. Given, let's say you're given the basis as a set of vectors which are not orthonormal. You're just told like the subspace is the span of these vectors. Like here's a matrix A. The subspace is the column space of this matrix, the span of the columns of A. Then how do you get an orthonormal basis? You do something like maybe Gram-Schmidt, or you do some kind of matrix decomposition. That's expensive. So we'd like ways of getting subspace embeddings which are not computationally expensive. I mentioned one is a sampling approach, which is leverage score sampling. We're going to see that today, more about that. And the other was oblivious subspace embeddings, where you pick kind of a random matrix that the distribution does not depend on the input subspace, on the input matrix, let's say, that you're taking the column space of. And then after I talk a little bit about that, I want to say more on regression. So I gave you one analysis already of sketch and solve, which said if you have an epsilon subspace embedding, you can use it to get approximate regression up to 1 plus epsilon. There are other things you can say that, other ways you can analyze even sketch and solve. You can say, actually, I don't even need an epsilon subspace embedding for sketch and solve. I just need a constant quality subspace embedding, like a 1/4 subspace embedding. And if I get that together with another property, which is going to be approximate matrix multiplication, that alone, those two things alone are good enough to analyze sketch and solve. And the other thing I'm going to talk about is a non-sketch and solve approach, namely an iterative approach using preconditioners. And then we're going to be done for today, and we're going to continue on Wednesday with more linear algebra stuff. So let's start off with item one, which is how to get subspace embeddings. So just remember the subspace embedding, an epsilon subspace embedding. What does that mean? It means that for all x, ax, I'm thinking of it as, say, the subspace embedding is like the column space of an input matrix A. So let's say like E is equal to the column space of A. So what does it mean? It means for all x, if you look at ax L2 norm squared, it's like 1 plus or minus epsilon times pi ax L2 norm squared, right? Then I'll say that pi is an epsilon subspace embedding for the column space of A, which is a subspace. And what is this thing? This thing is x transpose A transpose A x. So like this is the item here that matters a lot. Basically, we want to approximate A transpose A. And the observation was that A transpose A is equal to the sum of AI transpose, where I goes from 1 to n, where A is this matrix. So it's an n by d matrix, let's say. So the idea of sampling is, sampling. We write down a sampling matrix pi, which let's say we take m samples. Each row has a 1 in a random location divided by something to make it unbiased, say square root of pi, and then a 0 everywhere else, where like this is the ith column. And then the next row has a 1 in a random, a non-zero in a random location, and then zeros everywhere else, etc. Let's say there are m of them. So this is just row sampling, right? We're taking m independent samples of rows of A, right? And that's pi A. And the question then is, what should these, what should these probabilities be to get some kind of guarantees with good probability? And also I want to say that kind of pi A now, pi A transpose. Actually, we're not actually going to analyze this exact matrix. we're going to analyze something similar. It turns out you can analyze this too, but this one just is a little bit easier to write down and deal with. We're going to look at pi, which is actually a diagonal matrix with zeros on the off diagonal, and it's going to be n by n. And if you look at the ith entry, the ith entry in the diagonal, so this is I and this is I, that's going to be equal to, I'll call it eta I over pi, root pi. So eta I is equal to like 1 if we kept row I of A and 0 otherwise. And the probability that eta I is equal to 1 is going to be pi. So it's similar to what I wrote above. It's just instead of taking exactly m samples, we're going to take m samples like in expectation, right? Because really the number of rows that are getting sampled is just the number of etas, right? The number of rows sampled is equal to the sum I goes from 1 to n of eta I. It's just like which of the eta i's are 1, right? Which is a random variable. So instead of exactly sampling m rows, we're going to sample a variable number of rows that's a random variable, but we hope that, it's like, well, its expectation is going to be something that we're going to bound, and it's going to be concentrated around the expectation. So with high probability, we don't sample too many rows. So it's similar. Okay. And then now what I can write is I can write pi A transpose pi A, right, as the sum I goes from 1 to n, this is an n, not an eta, of eta I over pi AI transpose, which implies like the expectation of that thing is the sum of AI transpose of the expectation over pi, let's say, of the expectation of eta I. But of course, this cancels. That's why we divided by root pi. So this is equal to A transpose A. So this is an unbiased, this matrix is a random matrix, pi A transpose pi A, but its expectation is what we want. And now we want to say something about concentration. We want to say that with high probability, for all x, the quadratic form is preserved for this versus A transpose A. For all x, X transpose pi AX is very close to X transpose A transpose AX. So how do you get something like that? So I'm going to give a definition. The sensitivity, this is a technical term, of the ith row, let's call the sensitivity Ri. The sensitivity Ri of the ith row of A is defined to be as follows. Ri is the sup over all x of ai dot x squared over the L2 norm squared of ax. Right? If you think about what that means, that's the same thing as the sup over all x of ai dot x squared over the sum over all j from 1 to n of aj dot x squared, right? So ai dot x squared is one of those terms in the sum in the denominator, right? And the question is like, is there an x where the numerator is a really dominant term in the denominator sum, right? This ratio is of course always between 0 and 1. Okay. It can't be more than 1 because the numerator is part of the denominator, and of course it can't be less than 0 because everything here is non-negative. When is it going to be 1? It's going to be 1 if there is an x that's orthogonal to all the other rows, but not orthogonal to the ith row. So Ri is basically some measure of how important the ith row is, right? In the sense that I'm going to say that the ith row is important if there is an x where the ith row matters a lot in the quadratic form. Okay, so this is the definition of sensitivity. Now, let's try to build some intuition now from this definition. Let's try to build some intuition for what the PI should be. Now, I think it would be kind of weird for some PIs to be 0, because it's like, that means that I'm just ignoring part of the matrix. If I'm trying to preserve the quadratic form of the matrix, I probably shouldn't ignore any part of it. So I probably shouldn't be setting any PIs to 0. Again, I'm not being formal here. I'm just trying to build intuition. Now, if a PI is not 0, I claim, again, this is just intuition, if PI is not 0, so it's strictly bigger than 0, then we definitely need PI to be at least, let's say, R over 2. Okay. So I'm saying, like, if it's not 0, there's no point in making it super small, some epsilon. It needs to be at least Ri over 2, sorry. Why is that? Remember, we want a subspace embedding, right? So if it's not 0, then that means that, there are some cases where I am going to sample this row. And if I am going to sample this row, that means that when I throw a sampled, pi ax L2 norm squared is going to be at least ai dot x L2 norm squared over pi. Okay. And the point is, if pi is too small, then I claim that if I choose x to be the vector that maximizes the supremum in the definition of sensitivity, that particular x is going to get blown up too much. Remember, to be a subspace embedding, you need to preserve everyone's norm up to 1 plus epsilon. I claim that that particular x is not going to be preserved up to 1 plus epsilon. You're going to blow up his norm a lot, unless you set pi to be large enough. Okay, so let's say that x is actually the x star that achieves the supremum. Okay, what do I know about ai dot x star squared? That's equal to, right, just by rearranging the definition of Ri, x, now x star is the x that achieves the sup. ai dot x star squared is equal to ax star L2 norm squared, now times Ri, and then we had a division by pi. This thing here now is bigger than 2 times ax star L2 norm squared, unless pi is at least Ri over 2. Remember, we're trying to preserve things up to 1 plus epsilon. Here I'm blowing it up by a factor of 2, which I'm imagining is more than 1 plus epsilon. Wait, does that make sense? So I'm just trying to build intuition here to say, look, I mean, I don't know that setting pi to be Ri over 2 is good enough. But what I do know is, if pi is non-zero, then there's no point to setting it less than Ri over 2. Because, if you're setting it to be non-zero, that means that it is going to get sampled sometimes. And when it does get sampled, you're guaranteeing that you're screwed, unless it's at least Ri over 2, right? You're guaranteeing that you're screwed because x star in particular will be distorted a lot. Does that make sense?
Yeah, but I mean, so we could get like a tighter bound in terms of epsilon, but we're just taking this I over 2. That's
right. Yeah. So why don't I care about the factor of 2? I mean, notice that like the expected number of rows sampled is just the sum over I from 1 to n of the expectation of eta I, which is the sum of pi. Right? So, I'm just looking at how good is my sketch, how many rows am I sketching down to? And I just want to know that up to big O notation, right? So the point is, the expected number of rows in my sketch is the sum of the PIs. So ideally, I would like the sum of the pi's to be as small as possible. And what I'm saying is, like up to theta notation, up to big O notation, you're basically you shouldn't really hope to beat the sum of the ri's, right? You shouldn't hope to beat big O of like the sum of the pi's or ri's, because pi needs to be at least ri over 2. Does that make sense? Okay. I mean, it's not clear that we can achieve sum of ri, but I'm just saying, like, you shouldn't hope to beat it. That's sort of like, that should be maybe the target. Okay. So now the question is, like, okay, so I gave this weird definition of sensitivity. Like, what is the sum of the ri's? It's like the sum over I of the supremum of something or other. It seems kind of complicated. So let's try and give a different definition, which is the following. Sorry, 1 second. Okay, so I'm going to define something called the leverage score, and as it's going to turn out, so let's define leverage score. The ith leverage score Li is defined as follows. Li is just equal to AI transpose, okay, and then A transpose A pseudo inverse, okay, AI transpose, or AI, which of course AI is the same. AI is also known as, so again, think of it like, if I look at EI transpose A, right, EI is the ith standard basis vector. That's selecting the ith row of A. So AI transpose is the same thing as EI transpose A. And then I have A transpose A pseudo inverse. And then I have A transpose EI. If you don't remember from the last lecture, I said, what is the pseudo inverse thing? I said, look, there's this SVD of matrices. A is equal to U sigma V transpose. And the pseudo inverse is equal to, by definition, V sigma inverse U transpose. If this doesn't sound, if you're not remembering this, don't worry. I'm going to keep talking about SVDs and pseudo inverses a lot today and on Wednesday, and maybe even next week. So you'll get the hang of it. Again, U and V have orthonormal columns, and sigma is a diagonal matrix that has non-zero entries in the diagonal, strictly positive entries in the diagonal, and they're sorted. So the top, sigma 1, 1 is the largest entry in sigma. Sigma 2, 2 is the next largest. Sigma 3, 3 is the next largest. These are called the singular values of sigma. Okay. If A is a real symmetric matrix, then sigma just has the absolute values of the eigenvalues. So it's like the magnitudes of the eigenvalues, if you can think. Okay. So, anywho, now what I want to say is, if you don't remember, I'll remind you, this thing is just the orthogonal projection onto, I think, the column space of A. You can see that by looking at the SVD. So if you just expand this out, A transpose A is, let's do A transpose A is equal to V sigma U transpose U sigma V transpose. And then we're taking a pseudo inverse of that. And then we're taking A transpose, which is now again V sigma U transpose. And then we have an A, which is U sigma V transpose. If you just, U transpose U is identity because it has orthonormal columns. This is sigma squared. Now you take the pseudo inverse, and then you get V sigma minus 2 V transpose. That cancels with that. V transpose V is identity. V transpose V is identity. You have two sigmas and a sigma to the minus 2, so that goes away. And then altogether you have U transpose, right? You have only these two things survive. So it's the orthogonal projection onto the column space of A. So this is also just equal to, like, ui L2 norm squared, where u is, this matrix, u1 transpose up to like un transpose. Does that make sense? Okay. And now the claim is that, behold, linear algebra Ri equals Li. So even though this definition looks a little bit different than the sensitivity definition, it turns out they're actually the same thing. Okay. And now, why is that important? Again, remember, we were interested in understanding the sum of the Ri's, right? We said we can't hope to beat the sum of the Ri's as our number of samples, but the sum of the Ri's, because of that claim, is the same thing as the sum of the Li's, which is the sum of the squared norms of the rows of U. These are the rows, which is the same thing as, it's the sum of the squares of all entries in the matrix, basically. So that's just equal to U Frobenius norm squared, which is the same thing as the sum of the squared columns of the matrix. So let's say U superscript I is the column. What's that? First of all, there are D columns if it's a rank D matrix. What's this? Remember, in the SVD, U and V have orthonormal columns. Right? So each column has norm 1. Right? The columns are on orthonormal basis, so they have norm 1. So this is just the sum of 1 D times. So this is D. Right? So what this is saying is, we're not going to hope to beat. This is something I guess we already knew. We're not going to hope to beat D rows or O of D rows in our sketch. Okay. And let me skip. The proof that Ri equals Li is again just a change of basis thing. I'll just put it in the notes. It's not anything too important for this lecture, so I'll punt it to the notes. But kind of the miracle is the theorem, and this is due to Spielman and Srivastava, who's here in the math department at Cal. I believe this was 09, but maybe it was 08. It's anyway. I've already actually put this theorem in the notes. You can see the reference, which says that if pi is at least, let's say up to a constant factor, it's at least, let's say, the max or the min, not the max, the min of 1, and something like some constant times Li, the ith leverage score, times log of d over delta over epsilon squared, where d is, again, the rank of the subspace, is the rank of the column space of A, or the rank of A. Then the probability over pi that pi fails to be an epsilon subspace embedding for, let's say, for E, is almost delta. We're again here, this is the sampling matrix. Okay, so then the expected, sketch size, right, is equal to the sum of the PIs, which is equal to, according to this, big O of log d over delta over epsilon squared times the sum of the Li's, which is O of d log d over delta over epsilon squared. So it's not terrible. It's you can't hope to beat D, and this is getting within some log factor of D, log d over delta. Okay, so I think I'm not going to prove this. The proof uses something called we've talked about the Chernoff bound in class, and Bernstein's inequality. This is all in the probability review in the lecture notes. It turns out there are matrix versions of that too, where instead of summing independent numbers, independent scalar random variables, what if you sum up independent matrices where the matrices are random? What can you say about the sum of independent matrices concentrating around their expectation, let's say an operator norm? There are theorems that give you that kind of bound. For example, the matrix Chernoff bound, matrix Bernstein, non-commutative Khinchin inequality. So those things pretty much immediately prove this theorem for you. It's just a matter of plugging in the matrix version of the Chernoff bound, and you get the theorem. Okay. Now, you might be looking at this and say, wait a second. I mean, the reason I want a subspace embedding is that I can do faster regression or faster low rank approximation, etc. This theorem is saying I need to sample rows with probabilities that depend on the leverage scores. What are the leverage scores? The leverage scores are the squared row norms of this matrix U, right? This right here. These are the leverage scores. How do I know those? Do I need to know capital U? Well, how do I get capital U? I either do the SVD or I do some kind of Gram-Schmidt or something. But if I knew capital U, then why wouldn't I just pick my subspace embedding to be U transpose, right? Like, why am I doing all this other more complicated stuff? We already said that U transpose was the best subspace embedding you could hope to have. Okay. And the reason is that we're not actually going to sample with these probabilities. As long as you sample probabilities that are at least that large, that's good enough. So if I know, let's say, if I know the LIs up to a factor of 2, let's say, or up to a constant factor, then I can slightly oversample. I can pick my PIs to be maybe a factor 2 larger than they need to be, and then sample with those probabilities. And I can still invoke this theorem and get a good subspace embedding with high probability. And it turns out that even though computing the exact leverage scores is not so easy, because again, we don't know U exactly, getting approximate leverage scores, on the other hand, is actually doable fast. Okay, and you're going to see that on PSET 2, which is going to be released soon. One of the problems there is it's a multi-part problem that's going to guide you through an approach to quickly get approximations to all the leverage scores, and it's going to actually be via the JL lemma, via Johnson-Lewinström's. Okay.
Do not have a problem with like do the PIs need to add up to 1, right? If we just take them to be like bigger than we need to be, is that not a problem?
So the way that I've defined it, it's not that you're independently sampling rows in each step where like the probability to pick I is PI. PI is just the probability that it survives, right? So it's like for each of the n rows, I flip a coin with bias PI to determine whether to keep that row or not. So the PIs don't sum to 1. In fact, the PIs sum to something like D log D, or D log D over epsilon squared. Does that make sense?
Wait, would you not want them to sum to something less because you're trying to reduce it down?
Well, the original number of rows was n, right? Where n could be ginormous. Think of A as an n by D matrix.
Oh, okay. Yeah.
It has a ton of rows, and it has D columns where D is, I'm imagining, not as big. Then we're shrinking down the number of rows from n to close to D. So that makes me happy. Yeah. Okay. So that's all I wanted to say about sampling. And now let me talk about OSEs. Oblivious subspace embeddings. So how do you get those? Right? What do we want? We want that basically. Oblivious subspace embedding is a distribution D. Recall, it's a distribution D over m by n matrices. That's not very visible, legible. Such that for all U, which is an orthonormal basis for a D-dimensional subspace, so U transpose U is identity. U transpose U as identity means it's an orthonormal basis, right? It means the columns are an orthonormal basis because different columns have dot product 0, and each one, UI transpose UI is 1, which means that the ith column is 1, 1. So I want that the probability that pi drawn from D of pi U transpose pi U minus identity bigger than epsilon is like less than delta. So this is the definition of oblivious subspace embedding. So the question is, how do we come up with such a D? Okay. So this is the what the notion of epsilon delta D oblivious subspace embedding. Okay. So how do we get them? So one is via a net argument. So we can't just do JL here, right? I mean, yeah. So what is this saying? This is equivalent to we want to preserve the norm of every vector in the subspace. So JL says if you want to preserve, Q vectors, you can map to log Q dimensions. The problem here is Q is infinity. We're trying to preserve all vectors in the subspace. There's an infinite number of vectors in the subspace. So you can't really talk about log the number of vectors. That's infinite, log of infinity. So a net argument says, basically there exists a subset E prime of E such that if pi epsilon preserves all x prime and E prime, can show that implies pi O of epsilon preserves all x and E. And E prime will be like a 1/4 net of E of like, let's say the unit ball of E, unit L2 ball. Okay, so the size of E prime will be something like O of 1 to the dimension. So this implies that the number of rows you need is like big O of like log E prime over epsilon squared, which is O of D over epsilon squared. Right. This is now just DJL. DJL says if I map to dimension log 1 over distributional JL, if I map to dimension log 1 over delta divided by epsilon squared, I'll preserve any fixed vector with probability delta. Actually, I guess I should be a little more. If you want exactly this property, there's a delta in here, right? If you want exactly this property, then I should actually say that this should really be log the size of E prime. Log the size of E prime over delta. And then this will be big O of D plus log 1 over delta over epsilon squared. Okay, right? So distributional JL says, if I map to dimension log 1 over delta over epsilon squared, for any fixed vector, I'll preserve it with probability 1 minus delta. So now I'll just pretend my delta prime is actually delta over E prime. That way it's small enough that I can union bound over all the vectors in E prime and succeed with probability 1 minus delta after the union bound, right? And then I get basically this, okay? And the fact that the fact that, you can show that this implies that pi works for all of E, that's also going to be on your next homework. So that's with a little hint, but that's basically problem 1 on the next piece set as well. Okay. So that's the first thing, which is a net argument. So already, what do we know? We already know distributions that give DJL, right? We know that a random plus minus 1 matrix gives DJL, distributional JL. And you need log 1 over delta over epsilon squared rows. So that translates into exactly this bound. You'll have a oblivious subspace embedding with D plus log 1 over delta over epsilon squared rows. And for OSCs, it's known that this is optimal. This is optimal. That's due to me and Hui Guin. So if you want an oblivious subspace embedding, you cannot get rows fewer than that. We also know that sparse JL gives distributional JL as well, right? Where the column sparsity is a little bit better than a dense matrix. That would imply that the number of rows would be something like d over epsilon squared, but the sparsity per column would only be d over epsilon, right? So you can sparsify every column by a factor of epsilon. That just follows black box from applying sparse JL to the net. You could also do it with fast JL. Fast JL we've seen already. Also, the one based on the fast Fourier transform. That also gives you DJL. So again, that translates into a subspace embedding as well via this. Okay? So the net argument is one way to get subspace embeddings. It's not the only way. Another way that I'll say is, method number 2 is what I'll call the moment method. What's the moment method? Well, we're looking at this. What's the probability over pi that pi u transpose pi u minus identity is bigger than epsilon? Let me call this matrix M. We know that by Markov, this is less than the expectation of the operator of M to the P over epsilon to the P. I raised both sides of the inequality to the Pth power. Then I did Markov. Okay. And then now what I can do is I can say the following. This is actually less than or equal to the expectation of, and I'll define this, M Shetland P norm raised to the Pth power over epsilon to the P. So what is the Shetland P norm? Okay. Shetland P norm says it's the LP norm of the vector of singular values of M. Right? So remember again, we can write an SVD, M is equal to U sigma V transpose, where sigma is this matrix of singular values. So it has sigma 1 down to sigma D, the zeros all here. Sigma 1 is bigger than or equal to sigma 2, is bigger than or equal to dot, is bigger than or equal to sigma D. So the Shetland P norm is equal to the sum of sigma I to the P raised to the 1 over P.
So the operator norm is kind of like the Shetland infinity norm.
That's right. Yeah. So the operator norm is the same thing as like the Shetland infinity norm. That's right. Which is just sigma 1. Okay. And a nice thing to observe is when you have a real, okay, so now here's a little bit of linear algebra, right? So if you have a real symmetric matrix M, if M is real symmetric, then I can write M as Q lambda Q transpose, where this is an orthogonal matrix, right? So that implies that M to the P is equal to Q lambda to the P Q transpose, which means that the eigenvalues of M to the P are just, lambda 1 to the P up to like lambda D to the P, right? And what are the singular values? The singular values are just the absolute values of the eigenvalues, right? So the singular values of M to the P are just like the absolute value of lambda 1 to the P up to like the absolute value of lambda D to the P, which is equal to lambda 1 to the P up to lambda D to the P. Actually, is that, yeah, lambda D to the P if P is an even integer. Because if it's an even integer, then if it's negative, when you raise it to an even power, it becomes positive. And then I can then just say, like, basically Shetland P norm raised to the P. So this means that the Shetland P norm raised to the P is equal to basically the trace of m to the pth power. The trace, right? The trace of a matrix gives you the sum of the eigenvalues. The trace of a real symmetric matrix gives you the sum of the eigenvalues, which here is the sum of lambda I to the p, which is the same as the sum of sigma I to the p, because the sigma I to the p is lambda I to the p. So I can write this is equal to the expectation of the trace of m to the p over epsilon to the p. So the name of the game then is to basically bound this. Okay. How do you do that? Well, there are two ways now to bound the expectation of the Schatten norm to the p. So, let's say method 2a is like the combinatorics method.
And so we weren't assuming p is an integer before, but now we're assuming
p is an even integer now. So like, yeah, so p is an even integer. Okay. So if you look at, this is just a fact again about, linear algebra. If you look at a matrix, square matrix, take it to the pth power and look at the ijth entry. This is equal to the sum over all I1 up to IP plus 1, where I1 equals I and IP plus 1 equals J, of the product T goes from 1 to P of M, IT, comma, IT plus 1. You can prove this by induction on P. Okay, so this is just a fact about entries of powers of matrices. What's the trace? The trace is the case that I equals J. So this implies that the trace of M to the P is equal to the sum over all I1 up to IP plus 1, such that I1 equals IP plus 1 of that same product. Which means if you take the expectation, by linear expectation, you get this. And then, you try to just do it kind of brute force. So, it's going to depend. Remember what M was. M was pi u transpose pi u minus identity. So, depending on what pi is, you'll be able to write down something for the terms in this product. It'll involve some random variables because pi involves random variables. You'll compute the expectation, you'll get something, and then now you have to sum that something over all these basically paths from cycles basically, because you start at I1, you walk around and you have to land at I1. So it's like the sum over all cycles of something. And, it ends up being just basically a lot of combinatorics. So maybe I'll put a reference in the notes if you want to read how such things are done. But it just tends to be very involved calculations, as you might imagine, because there are like exponentially many summands here, and you have to somehow reason about kind of how many there are of different types and what those types are contributing, etc. 2b is something like, the non-commutative Khinchin inequality. Okay. So what does that mean? Let's just remind ourselves, like, what is Khinchin, first of all? Okay. And then I'll tell you what non-commutative Khinchin is. Right, so Khinchin says, if I look at something like the p norm of the sum of sigma I ai, this is at most root p times the L2 norm of A, where like A is a vector. So the non-commutative Khinchin tries to generalize this to matrices. It says, what if you have the operator of the sum of sigma I capital AI, where now capital AI is a matrix, and this is the p norm, sorry, this is the p norm. What's the p norm of a matrix? I'm just going to define the p, if Z is a matrix, the p norm, if M is a matrix, the p norm is just defined to be the expectation of the Schatten norm, the p Schatten norm to the p raised to the 1 over p. Okay. And then non-commutative Khinchin says that this thing is at most basically root p times the max of two things. It doesn't matter if the AIs are symmetric, but basically it's, on the one hand, the sum of AI transpose to the 1/2 P, and the other is the sum of AI transpose AI to the 1/2 P. And you might be looking at this and asking yourself, Jelani, what does it mean? What does it mean to take the 1/2 power of a matrix? In general, just an aside, if I have a function f which maps, let's say, non-negative, positive reals to positive reals, then when I write f of a, like a to the 1/2, it's by definition, what I mean is it's u f of sigma 1, f of sigma d, v transpose. So what I mean is take the SVD of A, apply f to its singular values, and keep u and v the same. This is now a new matrix, and this is what I'm calling f of A. So when I say take a to the 1/2, I literally mean take the same matrix A, but change its, take the square root of all of its singular values. So anyway, this non-commutative Khinchin has been proven, and it gives you something. You might look at this though and say, well, Jelani, this doesn't really look like our situation. We have the sum. We don't have a sum at all. We have pi u transpose pi u minus identity. Let's say Shat and P norm. But non-commutative Khinchin is looking at things of the form like the sum of sigma I AI, Shat and P norm. And actually, we don't even have Shat and P norm, right? I guess we do, right? We do, because that's what we did. That's what we did up here. We basically said what we care about at the end of the day is the Shat and P norm. So okay, so we have the Shat and P norm, but like this doesn't really look like the form that we want. It's not the sum of a random sign times some matrices AI. So like, how do you massage it so that non-commutative Khinchin actually applies? Well, just define Zi to be just define Zi to be the ith row of pi u. That implies that like pi u transpose pi u, is just the sum of Zi transpose. Right? We've already seen this before. In general, A transpose A is the sum of AI transpose. Okay. So then that implies that like, actually let me just write it like this. Pi u transpose pi u minus identity P norm. Remember how I defined the P norm of a matrix is just equal to basically the sum of Zi transpose minus the expectation of the sum of Zi transpose. Okay. Right? I mean, usually in all the cases that we are going to talk about in class, like we're always going to try to choose pi so that, pi u transpose pi u has the right expectation. In particular, its expectation is the identity. Okay. I mean, remember, u transpose u is the identity, right? So we're trying to pick pi so that pi u transpose pi u approximates u transpose u, but u transpose u is the identity. So we're picking pi's that give you unbiased estimators where pi u transpose pi u and expectation is the identity. So identity is just the same thing as the expectation of the random thing itself. And via basically symmetrization, this is going to be at most 2 times the sum over I of sigma I Zi transpose. So like, if you don't remember the symmetrization, this is in the probability review in the course notes. This is not specific to matrices. This is just kind of a general fact about, bounding p norms of deviations from the expectation. So this is called symmetrization. There's a lemma about it in the course notes.
So is this true for any?
Yeah, in general, if you have like the sum of like xi minus the expectation of the sum of xi, p norm, there's always at most 2 times the sum of sigma I xi.
Oh, sigma is still the singular values?
No, sorry. These sigma i's are random signs. So I'll call them ri's. All these sigmas are r's now. So ri is just plus minus 1. I should have said that here too.
Yeah.
This is.
Is that true for any ri's, or it's true in expectation?
No, it's true for ri is a random variable. It's plus 1 with probability at half and minus 1 with probability at half. Do you remember the Khinchin inequality? Right, this is Khinchin.
Yeah.
Right, Khinchin says if you take a random sign vector and dot it with a fixed vector a, you get moment bounds or entail bounds. And what I'm saying is there's something called non-commutative Khinchin, which gives you a very similar thing, but for matrices, and where you define p norm in terms of Shatton norms. Okay. And the thing, so you can do this, and basically you can massage. So now this is basically now your AI for non-commutative Khinchin. And then now that you have this, you can apply non-commutative Khinchin to this. You'll get something on the right-hand side that's still random because it depends on zi's, but there's some more work you can do and you can get everything to work out. So I don't want to go through this kind of meticulously, but all I wanted to say is there is a way to use non-commutative Khinchin to bound moments in terms of Shatton p norms. And another thing that I want you to keep in mind as well is like Holder's inequality. So we know when you have a vector, if you look at the L1 norm of A, that's always at least the L2 norm, which is always at least the L3 norm, etc., which is always at least the L infinity norm. Right? And of course, the same is true for Shatton norms, right? The same is true for Shatton norms because Shatton norms are just LP norms of vectors, namely the vector of the singular values. So we know that if you have a matrix, the Shatton p norm is at least, the Shatton infinity norm, which is just the operator norm. And we're relaxing the Shatton p norm. We're relaxing the infinity norm to the Shatton p norm, right? We're upper bounding the operator norm by the Shatton p norm. So you might ask yourself, like, why is this okay? Like, might we not be losing a lot via this upper bound, right? Upper bounding the operator norm by the Shatton p norm. But the thing to keep in mind is for vectors, a vector's p norm is basically the same thing as the infinity norm when p is at least like log of the dimension. This follows from Holder's inequality. I mean, if you want to see why, maybe I can just say this. In general, like the sum of, ai to the p, I equals 1 to n, is certainly at most, n times the max over I of ai to the p, which is just equal to n times the infinity norm of a to the p. And then now if you take the p norm, it means you're raising this to the 1 over p, right? Which means you're getting n to the 1 over p, that goes away, and then you have n to the 1 over p. And of course, n to the 1 over log n is also known as 2. If you don't believe me, just take the logarithm of both sides. The logarithm of 2 is 1. The logarithm of n to the 1 over log n is 1 over log n times log n, which is 1. And So that means that they both have the same logarithm, right? So that implies that basically when p is log n, the p norm and the infinity norm are the same thing up to a factor of 2. Does that make sense? So if you think about that in terms of Schatten norms, what's the vector that you're taking the norm of? You're taking the norm of the vector of singular values. How many singular values are there? It's the rank of A, which let's say is D. Let's say A has full column rank, so it's D. So basically, if you're taking the Schatten log D norm, the Schatten log D norm is the same thing as the operator norm up to a factor of 2. Right? So note the Schatten log D norm, where D is the rank of the matrix. Say D is the rank of M, is equal to the operator norm up to a factor of 2. So that, I just want to build your intuition. Like, that's why it's a reasonable thing to try. Like, why, that inequality that I did over here, bounding the operator norm to the P by the Schatten P norm to the P, you might look at that and say, okay, like that seems very, potentially loose. How can I hope to get good bounds that way? The intuition is, look, the Schatten log D, if I take P large enough, like log D, then the Schatten norm and the operator norm are basically the same thing anyway, up to a factor of 2. So I don't really lose much by doing that. And then I can leverage now properties of the Schatten norm to actually carry out the proof. Like, either use the fact that I can express the Schatten norm in terms of traces and then do some linear expectation, or use the fact that there are off-the-shelf bounds on the moments of Schatten norms, like, for example, the non-commutative Khinchin inequality. So, that's a little just more meta-analysis of like why we went the route that we went. Question?
On this page,
Here.
So like in the middle, those like P norms are like expectation of the Schatten norm to the P all to the 1 over P.
You mean like, for example, this one?
Yeah.
Yes.
And the 2 before it as well.
Yeah.
Okay. And so those are all random variables, like the pi is random.
Pi is random, right? That's my oblivious subspace embedding. That's my random subspace embedding. And z's are the rows of pi. The zi is the ith row of pi u. So since pi is random, z is random. So this is a sum of random matrices. Yeah. So does this all make sense? Does anyone have any questions? Okay. So good. And now maybe there's a third way that's related to the second way of analyzing oblivious subspace embeddings, which is via approximate matrix multiplication with respect to the Frobenius norm. Notice that, M Frobenius norm is always at least M operator norm. M Frobenius norm, by the way, is also known as the Schatten 2 norm. Okay. We already said that M operator norm is Schatten infinity. Frobenius is Schatten 2. So Frobenius norm is bigger than operator norm, or it's at least as big as operator norm. So if we want, it suffices to have probability of pi u transpose pi u minus the identity Frobenius norm bigger than epsilon is less than delta. If we add that, well, then we'd be great for operator norm too, because we're saying that even the Frobenius norm is small with high probability. The operator norm is only going to be smaller. So the Frobenius norm is at most epsilon. The operator norm is also going to be at most epsilon. Okay. And now how do you get this? Notice again that this is just equal to u transpose u. So this is exactly approximate matrix multiplication. with respect to Frobenius norm. And we already talked about that last week. Can get this via, for example, the JL moment property. Example. Oh, and by the way, normally in the JL moment property, you would have like, not in the JL, in approximate matrix multiplication, you would actually have times the norm of A times the norm of B. So that'd be times the norm of A, which is U, times the norm of B, which is just U again, so squared. Right? That would be AMM. The problem, though, is like we don't want that Frobenius norm squared there, right? We just want epsilon there. So what I'm actually going to do is I'm going to make this epsilon prime, and I'm going to make sure that epsilon prime times Frobenius norm squared of U is epsilon, which means I need to set epsilon prime to equal epsilon over the Frobenius norm squared of U. What's the Frobenius norm squared of U? We've already actually seen this earlier in lecture.
Is it D? Whatever the dimension?
It's D. It's the dimension of the subspace. You can see that by, so UF squared means you sum the squared entries of U. So just imagine doing it column by column. Right? We already said this earlier in lecture. Each column has norm 1. So when you square the norm of a column, it's 1. And you're summing that over all columns. There are D columns, so it's D. So this is epsilon over D. Right? So basically, we need AMM with error parameter being epsilon over D. So, for example, if you take the count sketch, it needs only one non-zero per column. And M can just be big O of like 1 over epsilon prime squared delta, which is big O of D squared over epsilon squared delta. Right? So the nice thing about this pi, it lets you multiply pi A very fast because pi is an extremely sparse matrix. So you can multiply pi A in time proportional to the number of non-zero entries of A. Number of non-zeros. So N and Z. And in fact, kind of the first paper to observe that you can use the count sketch in this way was Clarkson and Woodruff. In 2013. They actually didn't observe, they didn't realize that there was such a simple analysis. They ended up having like this, 8-page analysis that did a lot of complicated stuff. But it really just follows from approximate matrix multiplication, as you've seen here. And another way to get it is, and if you think about how do you prove that the count sketch has the JL moment property, it's basically a variance bound, which means the second moment. It's like taking P equals 2. So another way to show that this ultra sparse matrix works for subspace embeddings is just to do what we did over here, the moment method. You're actually, the moment method where you move to Schatten norms. Okay. And just take the second moment. So, so I'll write, or just do moment method on the second moment. P equals 2. Maybe I'll add that to the P set too. It's like a paragraph long proof. It's very simple.
So this is saying we can use count sketch for doing
subspace embeddings. Oblivious subspace embeddings. That's right. And you get an ultra sparse subspace embedding. I should mention that you can also do, maybe I should have said that when we were talking about the moment method. PS, you can analyze sparse JL for subspace embeddings using the moment method also. Oops. What I mean is, method one was do a net argument. Method two was let's bound chat and p norms to the pth power. If you do a net argument on sparse JL, remember sparse JL. Sparse JL says pi looks something like this. It's basically the count sketch. It says, divide up the rows into blocks, and then in each column, you pick a random entry per block to be a random sign. Right? And you have S blocks. So S non-zeros per column. So a net argument would say, like, pick M to be D over epsilon squared, S to be at least D over epsilon. But if you do the moment method, in fact, you can get something like M to be at least D polylog D over epsilon squared, and S is like at least polylog D over epsilon. So this was due to myself and Hui Win. Try 13. Or there's some follow-up works with some improvements to C. Kind of the state of the art here is you can get M to be at least D log D over epsilon squared. And actually, let me put the deltas in here too. So D log D over delta over epsilon squared, where S is at least log D over delta over epsilon. And then there's a conjecture that this is like almost optimal, that times should be a plus. So it should be that M is at least something like, should be like D plus log 1 over delta over epsilon squared with the same level of sparsity. But unfortunately that conjecture is still open. So, that'd be nice to resolve at some point. It might be a little too hard for a class project, but anyone who's interested in a good problem, that's open.
Is this for oblivious subspace embeddings?
This is specifically analyzing sparse JL or the count sketch, for OSEs. Like, what M and S do I need to, how should I set M and S in the count sketch to give me the OSE property I want? And the claim is, if I pick M to be this, the conjecture is if I pick M to be this and I pick S to be the same S as Cohen. Oh, and I forgot to say that the reference for this is due to Cohen, Michael Cohen, in 2016. The conjecture is that this works.
And so this is like slightly sacrificing like the number of rows to make it more sparse?
I'm not sacrificing. Well, the conjecture says that you don't need to sacrifice anything because this is the same number of rows as a dense random sign matrix. So the conjecture is that even with a count sketch, I can get away with the same, up to a constant factor, the same number of rows as a dense matrix, but with like exponentially better sparsity, column sparsity. Because instead of D, it's log D. Does that make sense?
But it said there's the net argument said you can get D over epsilon squared.
Yeah, well, if you factor delta into it, it's like D plus log 1 over delta.
Okay.
And here it's like D plus log 1 over delta.
It's like the current ones do sacrifice, but the conjectures that you don't have to sacrifice.
That's right. Yes. Okay. So I think that's all I wanted to say about OSEs and how you get them. So basically, there's the net argument and there's the moment method. And there is also the AMM, via AMM, but that's really just the moment method again, because the way that you get AMM is via the moment method too, right? So it's just kind of sugar coating the same kind of approach. So good. So now you know like where OSCs come from, and you're going to actually carry out the net argument on the P set, so you'll get more hands-on practice with that, and really understand why it works. But now I want to say more about regression. So last week, more on regression. So last week, we did sketch and solve. So I said that beta tilde ls is just going to be the argmin of pi x beta minus pi y L2 norm. And then the claim was pi is an epsilon subspace embedding for E, which is the span of y in the columns of pi, implies that pi beta tilde ls implies that x beta tilde ls minus y L2 norm is at most 1 plus epsilon over 1 minus epsilon times x beta ls minus y L2 norm. So in other words, as long as pi is an epsilon subspace embedding, which we know, for example, that could be like d squared over epsilon squared rows via the count sketch, or we know it could be something like d over epsilon squared rows via like a dense random matrix. That's what we just saw. This is what we just saw a few moments ago, right? How do you actually get subspace embeddings? Well, the count sketch gives it to you, for example. So as long as pi is an epsilon subspace embedding for a certain d-dimensional subspace, or d plus 1 dimensional subspace, then you'll get sketch and solve will give you a good result. Now, it turns out that today, so I'll show you, there's a different way. So Charloche has a different way of analyzing sketch and solve. He says that actually you only need that pi is let's say 1/4 some constant subspace embedding of column space of x. Okay. And he needs that pi provides something like root epsilon over d approximate matrix multiplication with respect to the Frobenius norm of like 2 specific matrices that arise in the analysis. So if you think about it now, if you want the count sketch to be a 1/4 subspace embedding, how many rows do you need? You need d squared rows. D squared over a quarter squared, which is big O of d squared, because a quarter is a constant. If you want AMM from the count sketch, let's say you want alpha error from the count sketch, how many rows do you need? You only need 1 over alpha squared, right? Which means, alpha here is root epsilon over d, so 1 over alpha squared is just d over epsilon. So this only needs O of d squared plus d over epsilon rows in the count sketch, for example, which is less than above. Above was d squared over epsilon squared. Here, the epsilon doesn't even need to multiply the d squared. It only multiplies d, and it's only epsilon. It's not epsilon squared. So it can give you better sketch results. And then also another approach is basically preconditioning to speed up gradient descent. Okay. So let me show you these analyses, so you can see like another way to use the subspace embeddings without, with getting a better number of rows. Okay. So Charlotte approach. Okay. So let's write now beta ls is the argmin, right, of x beta minus y. And I'm going to write beta tilde ls is the argmin of pi x beta minus pi y. Okay. And let me write the SVD. X is equal, so this is just all notation to set up the proof. X is equal to u sigma v transpose. And I'm going to write that x beta ls. Okay, so remember now, the columns of u form an orthonormal basis for the column space of x. So I can, no, so x beta ls is in the column space of x. So I can express it as u times something. So I'm basically defining alpha here, okay, for some alpha. And then I can also write, let me define w as, I'm just going to define w as y minus a beta ls. Y minus a beta ls. In other words, like opt is equal to the norm squared of w. So let me write this as, like, I'm trying to minimize. I want to minimize. It doesn't really matter. Let me just square it. I want to minimize the norm of x beta minus y L2 norm squared. So then opt is the norm squared of w. And let me finally also make another definition, which is that x beta tilde ls minus x beta ls. Again, this is the same thing as x times quantity beta tilde minus beta. So it's in the column space of x. So I can write it as u beta for some beta. So, okay, I apologize. That was a lot of notation. Let's now try to understand what I can say about x beta tilde ls minus y. Right? This is the thing that I'm hoping is close to opt. Because this is beta tilde ls is what I got from Sketch and Solve. I solved the Sketch version of the problem. I got beta tilde ls. I would somehow like to now relate this to opt. So what I'm going to do is I'm going to add in beta ls and subtract it. So this is equal to x beta tilde ls minus x beta ls. I'm going to stop writing the ls because it's or actually, oh, and I just realized, let me not use beta. Let me call it, because beta is already, give me another Greek letter, rho. A rho looks too much like p, gamma. Okay, so let me stop writing all the LS's. If I don't write LS, it's there. So I'm subtracting x beta and I'm adding it back. So this is plus x beta minus y, L2 norm squared. Now, in general, if I have this is a plus b, let's think. If I have a plus b L2 norm squared, I can express it as a squared plus b squared plus twice the dot product, right? I claim that a dot b is 0. Why? Because a is in the column space of x. What can you tell me about b? Well, beta is the optimal solution to least squares. What's the optimal solution to least squares? It should kill the part of y that's in the column space of x. So the only thing that survives after you subtract is the part of y that's in the orthogonal space. So x beta minus y is orthogonal to the column space of x, which means that b is orthogonal to a, so the dot product is 0. So this is equal to x beta tilde minus x beta squared plus the norm squared of w. That's the definition of w, which is just opt.
The
And
definition of W dot A should be an X.
W dot A is 0. Oh, sorry, yeah, I guess B and W are the same thing. Sorry, does that make sense? So I guess I could have just called this W.
Oh, yeah.
W, by definition. Oh, and what is A? There's no A. There's X. Is that what you meant?
That's what I meant. Sorry.
Yeah, sorry. And this is by definition the square norm of U gamma, which by definition is the norm of gamma. Well, not by definition, but remember U has orthonormal columns. So this is the norm of gamma because U transpose U is identity. So the name of the game is to show that gamma has small norm. And for this, we're going to use the approximate matrix multiplication property, and we're going to use subspace embeddings. Okay. So now, how are we going to do that? Okay. So first of all, let's look at pi u, okay, times alpha plus gamma. Okay. Now, what is the definition of alpha? You know, U alpha is x beta. U gamma is minus x beta plus x beta tilde. So just by definition, this is equal to pi times pi times x beta tilde, I guess, right? Okay. Now, what can I tell? What do I know about x beta tilde? X beta tilde, remember, beta tilde is the optimal solution to the sketched version. So x beta tilde kills off the part of pi y in the column space of pi a. So this had better be, so x beta tilde, or pi x beta tilde, sorry, is equal to the projection onto the column space of pi x of pi y. Okay. And this is the same thing as the projection onto the column space of pi u of pi y. Okay. And then now I can again just write, you know, what is the, I can use the definition of W. W is y minus x beta. And U alpha is x beta. So I can write y as W plus U alpha. So I'm just going to rewrite y. This is equal to the projection of pi u of pi U alpha plus pi W. Okay. And projection, orthogonal projection is a linear operation. So this is the projection of pi U alpha plus the projection of pi W. What's the projection onto the column space of pi u alpha? Okay, it's just pi u alpha. So this is pi u alpha plus the projection of pi w onto pi u. And now magic, this pi u alpha cancels this pi u alpha. So what I have is that at least when you project onto the column space of pi u, pi w and pi u alpha behave the same, which implies that pi u transpose pi u gamma is equal to pi u transpose pi w. Okay, so let's take that away. So let's write that. That's an important fact. The fact here is now pi u transpose pi u gamma is equal to pi u transpose pi w. Now let's write the following. I know that pi is a subspace embedding. So that means that pi u transpose pi u minus the identity is at most epsilon. Is at most, let's say a quarter. So let's call it epsilon naught. It's some fixed constant. Let's say it's a quarter. Which implies that all the singular values of pi u transpose pi u are like 1 plus or minus epsilon naught. which implies that all the singular values of pi u, actually, I guess that's all I really need to say. So let's just say that. So what does that mean? That means that if I look at the norm squared, the norm squared of pi u transpose pi u gamma, and look at the norm squared, it's at least the norm squared of gamma times the smallest, basically, I guess I want to say like, yeah, I guess what I want to say is, yeah, times the smallest singular value of this matrix. Let's call this matrix B. Right? Which is like 1 minus a quarter. Which this thing here is like omega 1. So this is at least, some constant, like let's say 0.5 or something times gamma squared. On the other hand, this is equal to pi u transpose pi w, right? Because of the thing that I highlighted in red. Which is equal to pi u transpose pi w minus u transpose w. Why? Because again, this is 0. Remember, the optimal choice, what if you look at the definition of w is like, what is x beta? W is like, what is x beta minus y? X beta ls minus y. X beta ls minus y is the part of y in the orthogonal space to the column space of x. So it's orthogonal to the column space of u. So u transpose y is 0. W is orthogonal to the column space of u. Okay. But now again, this basically looks exactly like what? Approximate matrix multiplication. This is the matrix, this is u transpose w, where u is a matrix and w is like w is a matrix too. Vectors are matrices, right? W is like an n by 1 matrix. Okay. So by the approximate matrix multiplication property, this is at most epsilon prime times the norm squared of u, for Beane's norm squared of u, times the norm squared of w. Okay. And again, this is also squared, because since there's a squared here, I'm squaring everything on the right-hand side. Epsilon prime was root epsilon over d. So this is epsilon over d times d times opt. D's cancel. This is equal to epsilon times opt. So what have I just shown? Combining everything. 0.5 times gamma squared is at most epsilon times opt, which implies that gamma squared is at most 2 epsilon opt. So if you go back, we said that the quality of beta tilde is equal to opt plus gamma squared, which we just said now is at most opt plus 2 epsilon opt. So that's 1 plus O of epsilon times opt. Does that make sense? So we managed to use approximate matrix multiplication in combination with subspace embeddings to give a different analysis of sketch and solve. Okay. And we're out of time, so I won't have time to talk about the analysis, the iterative method. Maybe I'll talk about that at the beginning of Wednesday. But we'll talk about that, and then we'll start talking about low rank approximation. So any questions for me? And let me stop recording.